Alright, let's talk about actual, real, concrete rings, which, not really my thing. I don't know. These are just more like words and like collections of symbols rather than like functions. Like, when you do an analysis course, you can actually like see the things that you're working with. Here it's like the ideal generated by x squared, xy. Like, it's just linear combination. It's just like strings of symbols, and I feel like it doesn't have any like real interesting like depth to it. But anyways, at least improving things about it, like you get to use sort of, I guess, the more interesting facts and tools about ring theory. So that isn't so bad. All right. So first of all, we have this polynomial ring, K, this ring of polynomials in two variables, and K is a field. Now, if we take this and mod out by the ideal generated by x and y, then all we're going to be left over with is K. So we take a ring and we mod out by an ideal and we get a field. That's the same thing as this ideal being maximal. All right. So, oh, by the way, we're proving this C, then A, then B. I don't know why it was listed in this order if we're proving it in this order, but I don't know. Anyways, so the element x squared is in Qn because Qn is... Oh, by the way, this n greater than or equal to 2, 1 works as well. Yeah, x squared is in Qn because that's one of the generators, so x is in the radical of Qn because there is a power of x which is in Qn, i.e. 2. Alright? So x is in the radical of Qn, and similarly, there is a power of y which is contained in Qn, and therefore y is in the radical of Q. So therefore, x and y are both contained in the radical of Qn, so the ideal generated by these two elements is contained in the radical of Qn. So, since this ideal generated by x and y is maximal, the fact that this is contained in R of Qn means that R of Qn must be contained in this ideal since it's maximal. Well, is it obvious that this cannot possibly contain 1? Because this is an ideal generated by polynomials, and none of these polynomials have a constant term. So this can't possibly contain 1. Yeah. Okay, so therefore the Qn is not... Oh, well, you also have to consider powers of things, but you can't take one of these things to a power and get, like, a constant term. Is there anything else? Well, I guess you could multiply by a polynomial which has a constant term. No, but if you multiply by a polynomial which has a constant term, then you end up with... The thing you end up with still doesn't have any constant terms because the constant terms would be multiplied by these some power of x and some power of y. Some power of x or some power of y. So therefore, this ideal contains no constant terms other than 0, of course. So therefore, in particular, it does not contain 1, so it's not everything. So the fact that it is contained, or the fact that it contains a maximal ideal means that it must be the maximal ideal. So, therefore, the radical of Qn is the ideal generated by x and y. Okay, so that's C. And then part A is really easy because one of the problems in this problem set, which I referred to in problem 5, and also mentioned there that I probably won't put it up unless the proof happens to be really easy and I feel like it, which I probably won't, but maybe I will. Who knows? If you have an ideal whose radical, or if you have a ring whose radical is maximal, then the ideal is primary. I.e., I literally just wrote that out. Any ideal who... any ring whose radical is maximal must be primary. And hence, Qn is primary, because the radical of Qn is maximal. Alright, so that's A. And then all we have left is B. We want to prove that we have containment in both directions here. Alright? Now certainly this generating set for A is contained in the generating set for Qn, so A must be contained in Qn. Also, x squared and xy are both contained in the ideal generated by x because they both have factors of x in them. So therefore, Q, what is Q? Should be A. What was I doing? Okay, so both generators of A are contained in the ideal generated by x, and so A is contained in the ideal generated by x. So A is contained in both Qn and the ideal generated by x, so it's contained in the intersection. Now for the reverse direction, consider an element. Now I could have wrote this more clearly. Anyways, so this is how you write an arbitrary element of Qn. Of course, Qn is just finite sums of these things multiplied by coefficients in this polynomial ring. But you could just combine like terms to make it look like just some polynomial a times x squared plus some polynomial b times xy plus some polynomial c times y to the n. So here a, b, and c are in the polynomial ring. So anyways, this is an arbitrary element of Qn. Suppose that it's not only in Qn but also in x. So now we want to prove that this is an element of A. So we know it's in Qn, we know it's in Qn and in X. But the fact that it's in Qn allows us to write it like this, but we got to use the fact that it's in the ideal generated by X somehow. So since this is an element of here, X must be a factor of each term, because otherwise it wouldn't be in the ideal generated by X. Therefore, okay, so ax squared has an x in it, bxy has an x in it, cy to the n does not, a priori, you don't see an x there, but since x must be a factor of this, there must be a factor, okay, the x can't be in the y to the n, so it must be in the c. So there must be some, let's call it d, in the polynomial ring, such that c is just d times x. We're just writing c so that we see this factor here. So anyways, so then we can write this element as ax squared plus bxy plus d, and now we have an x and a y, and then we have y to the n minus 1. So we have a factor of xy in here. So x squared is in the generating set for A, but these two, because both of these now have have xy in it, they're both generated by this element in A, and so therefore this sum is in the ideal generated by this generating set, i.e. this sum is in A. So therefore this intersection is contained in A, and hence we have equality, and that finishes up the proof.